Hey there, everyone. Um, I hope the exam went well on Monday. Um, we are actually getting really close to the end of the third quarter, believe it or not. We only have a few weeks left here, which is pretty surprising. Just as a review for this week, um, today we're going to be finishing up Chapter 6. Chapter 4. We only have one section, Section 4.6 left. And then tomorrow and next week, we're going to be tackling Chapter 5. Now, Chapter 5 is a little weird because we've actually gone over some of the material already. I pulled some of it earlier. So we're going to actually go through Chapter 5 pretty quickly. A lot of it's on exponential and logarithmic functions. There won't be a quiz tomorrow, obviously, because we had a test. We had a test on Monday. I'll try to get those tests graded and back to you as soon as possible. So let's jump into the last section of Chapter 4. This is Section 4.6 on numerical integration. Okay. Now there aren't a lot of new concepts that we're actually going to go over here, so hopefully that should be that should settle some things for you, make you feel a little better. To again motivate what it is that we're doing here, all of Chapter 4 is really basically how do we find the area under a function from A to B. Okay. And what we determined from the fundamental theorem of calculus was that if I could find an antiderivative, so if I'm looking for an antiderivative capital F, then this is very, very easy for me to do. It's very easy for me to find areas if I can find an antiderivative. But let me ask a question. What if I can't find an antiderivative? Other than I cry or frowny face. Maybe I should put a little tear here. Make a little tear there. Now, this is actually a very relevant question, in part because I want to ask another question, which I'm going to actually come back to in Chapter 7, which is the question, can I always find a formula for the antiderivative? We know that every continuous function has an antiderivative. The question is, can I always find a formula for one? And the answer here turns out to be no. Not all functions, even if they're continuous, have nice antiderivatives. And what I mean by nice is actually you can write it down in a formula of some kind. So, for example, sine of e to the x is actually an example of a function that does not have a very simple antiderivative. Another one is e to the x squared. Now, why that is, we'll explore that a little more in Chapter 7. But there are functions that when I write them down, there is no nice formula for me to actually be able to find that gives me something that I can differentiate to get this back. There actually is none. Now, I'm not going to prove that here. But there are some functions that just don't have nice antiderivatives. So in this case, if I were to say, well, what's the area under this function from 0 to 1, if you're trying the fundamental theorem of calculus, that's not going to work here. So the question is, how do I get that area? Is there a different way for me to do it? Kind of a related question, so this is a first question. Kind of a related question is, how does your calculator compute integrals? Believe it or not, your calculator, depending on the kind of calculator you have, your calculator can actually do integrals. So if you have your calculator, go ahead and pull it out for a second. I want you to go ahead and turn it on. I'm not sure what, I'm trying to remember what kinds of calculators you guys had. If you go ahead and hit the math button and then scroll down until you hit a function that I think is going to be called fn int, which means function integration. I think it's actually functional numerical integration. We'll talk about what is numerical integration in a second. But if I wanted to get, for instance, the integral from 0 to 1 of x squared dx, what it'll actually do when you hit that fn int button is it should give you an integral sign with 2 boxes, another box, and then a d box. Okay, what you do is you fill in, it'll start you with this lower limit. You just put the number there, go to the right, and it'll flip you up to the upper limit. Put a number in there, then put a function in here, and stick your x in the dx spot. And if you hit enter, when you're done with that, if you do this integral right here, which we can actually do by ourselves, you should get 0.33333. Okay, so your calculator can actually do integrals. But you might be surprised to know that your calculator does not do antiderivatives. So how is your calculator computing integrals if it can't do antiderivatives? Well, if you think about how we answered this question before we did the fundamental theorem of calculus, the answer to it is we use rectangles to approximate. And if we get the answer as close as we need it, then that's good enough. Okay, we may not get an exact answer if we have an integral like this that we actually can't get an antiderivative for. We may not get an exact answer, so we're never going to, if you think about how we did this before, we would cut up things. I'm going to go over this again, but I would cut up things, find areas of rectangles, and then let n go to infinity. In this case, we're not going to let n go to infinity. We're just going to choose a big enough n so that we get a nice approximation. Okay. So approximating an area using rectangles, this is called numerical. Do this in a different color here. This is called numerical integration. Can you see that? That's pretty bad. Let's not do that. Let's see if I have a better pen. There we go. Numerical integration. Okay. The idea of numerical integration is that you just use a specific number of rectangles, like we might use 4 or 10 or whatever, and you approximate the area using that, and it's good enough. Does that make sense? So let's do, today we're actually going to look at several different ways to do this. We're going to use rectangles, and then we're going to make it a little fancier, but not too much fancier. So it's not going to get crazy, I promise. Okay, so the first thing that I want to do is I want to review what we did before when we were doing rectangles. We're going to do rectangles in 3 different ways. So let's start with so we're going to approximate first by using, so we're going to start with rectangles. Okay, and to do this, I'm going to draw my function and my interval from a to b, and I'm going to do it fairly big here. So again, my steps were to cut up the interval into n equal pieces. Okay, and then the width is b minus a over n. I'm just going to keep that width as delta x, but you can keep in the back of your head that that width is b minus a over n. So I'm going to cut this up into n equal pieces. And I'm going to label this first one x0, the second one x1, the third one x2, x3. The last one's going to be xn, so the one before that is going to be x of n minus 1. Right? Okay. So here's my function. All right. So then we choose where we're going to take the heights of the rectangles. And then we draw those rectangles. So we've done that with right endpoints. Okay, we're going to look at a couple of other examples today. But we pick, like, if we're going to take this first rectangle, if the height's going to be, by plugging x1 into the function, the height here is going to be x2, etc. Then we add up the areas of the rectangles. And then when we were doing this to find the exact area, the definite integral, we would let n go to infinity. Okay? We're not going to do that step here. We're gonna have a fixed number of pieces, like 10, or some specific amount. Okay? So let's do, starting with rectangles, let's first talk about right endpoints. Okay, we're going to do rectangles in 3 different ways. The first way is right endpoints, and we're used to doing this, so this shouldn't be too crazy or shocking. But I want to just draw this for you here. Okay. Again, I cut this up into n pieces. The first A is we're going to call x0, and B we're going to call xn. So we have x1, x2, x3. All right, and so we're going to take our heights to be the right endpoints, which means I'm going to take x1 and plug it in the function, then x2 and plug it in the function, x3 and plug it in the function, etc. Okay, so the area of the rectangles, when I use right endpoints, again, the R means right, and this is n rectangles. So R sub n. So the first rectangle is width delta x, and the height is what I get when I plug, if I'm taking the right endpoint, then I'm plugging in x sub 1. Okay. The next rectangle has width delta x, and height, what I get when I plug on this rectangle, I'm plugging in the right endpoint, so I'm plugging in x2. Okay. The next one's going to be delta x, and then I'm plugging in x3. And then the last one's going to be delta x, and what I get when I plug in x sub n. Okay. So in other words, if I pull a delta x out, it's going to be f of x1 plus f of x2, all the way up to f of x sub n. And I could put that in sigma notation. I'm just going to, for now, I'm just going to leave it like this. So R sub n, this is my formula for R sub n. So if you were going from 1 to 5, each of these this has width 4, so each rectangle is going to be 4 over n, so you'd have 1 plus 4 over n, so if n was 10, 1 plus 4 over 10, 1 plus 8 over 10, 1 plus 12 over 10. Those are the things you're plugging into the function, okay? There shouldn't be anything weird here. This is what we've been doing. We're just doing it, we're just reviewing it. Now I don't have to use right endpoints, I could use left endpoints. Okay. So the picture there going from A to B. Again, this is x0, 1, 2, 3, 4, 5, 6, etc. Okay, the last one's xn. I'm going to call this x1, x2. The one before the last one is x sub n minus 1. So what I'm going to do is I'm using right endpoints this time. Sorry, left endpoints this time. Okay, and the last one looks like this. Okay, so the area here, we're going to call this L sub n. So the L stands for left endpoints. And again, we're using n rectangles. So that first rectangle, again, has width delta x. But the height now, instead of being determined on the right side of the end point, the interval, it's on the left side of the interval. So the first height is going to be taken at x0, which is going to be at that point A. Next rectangle has width delta x, and the height is going to be what I get when I plug in x1. Then when I plug in x2, and then finally, what I get when I plug in the left endpoint on this last interval, that's going to be x sub n minus 1. So the formula for L sub n, if I pull out a delta x, is going to be f of x0 plus f of x1 plus f of x2 all the way up until f of x sub n minus 1. Okay, right and left endpoints are very common. There's also another common one that we often use, and it's called midpoints. So let's we'll go ahead and do midpoints over here. Okay, so let me draw my picture here. Again, x0, x1, 2, 3, 4, etc. Last one's xn. Okay, that's x sub n minus 1. Okay, what we mean by midpoints is the point halfway in between on these intervals. That's the thing I'm going to use to plug into the function. Okay, so instead of using the left endpoint, so here I would be way over, or instead of using the right endpoint, so here I would be under, I'm going to use the midpoint because the midpoint actually ends up giving me a nice approximation because part of it ends up being under, part of it ends up being over. Now, first of all, that midpoint, let me just blow this up for a second. Let's just take this first interval here. Here's x0, and here's x1, and I want the point halfway in between. Well, it turns out the point halfway in between is actually the average of the two. So it's x0 plus x1 over 2. Like if this were 3 and this were 5, the point halfway in between is 4, and that's actually the average of those two numbers. Okay, so what we're going to be doing is on each of these intervals, instead of plugging in the left endpoint or plugging in the right endpoint, we're actually going to plug in the average of the two. Okay, so for example, well, in general, if I want my area is going to be mn, so m stands for midpoint. And again, I'm using n rectangles here. So the first rectangle is going to have width delta x, but the height is going to be what I get when I plug that midpoint into the function. Now the midpoint is halfway in between x0 and x1, so it's going to be the average of of those two, f of x0 plus f of x1 over 2. It's the average, it's halfway in between those two. The second rectangle is going to have width delta x, and the height is what we're going to get when we plug in the middle point between x1 and x2. That's the average of x1 and x2. The next one is going to be what we get when we plug in the average of x2 and x3. And that's going to keep going until we hit delta x times the average of the last two, x of n minus 1 plus x of n over 2. Okay. So pulling out a delta x, we get f of x0 plus x1 plus f of x1 plus x2 over 2, all the way up until this last, so n minus 1 plus x of n over 2. Okay? So again, none of this should be too crazy. And the kinds of problems that you would get from a homework assignment, like what you're going to see in this section, is simply, like if I gave you, for example, the integral from 1 to 3 under square root of x dx. I could say compute this exactly. So if I asked you to compute this exactly, what I'm asking you to do is use the fundamental theorem of calculus. Okay, this is x to the 1/2, so it's now going to be x to the 3/2, and I'm going to have 2/3 here from 1 to 3. So I first plug in 3. 3 to the 3/2 is 3 root 3. And then 2/3, 1 to the 3/2 is just 1. So I'm going to have 2 root 3 minus 2/3. That's going to be my answer, whatever that is. Okay. Now, then the book could then say, okay, compute R4, L4, and M4. Okay. What they mean by that, R4, L4, and M4 means that if I have this function from 1 to 3, the square root function, and I want the area under it from 1 to 3, which we actually know exactly what it is, but we're going to approximate it. The R4, L4, and M4 mean I'm going to use 4 rectangles here. So this is going to be 1.5, this is 2, and this is 2.5. The right endpoints, according to this formula, what I'm supposed to do is I'm supposed to take the width of each rectangle, which the width is just 1/2, right? Each rectangle here is just 1/2. The R4 means there's 4 intervals. Overall, it was 2 wide, so each one's going to be 1/2 wide. So it's going to be 1/2 times f of x1. Remember, this is x0, x1, x2, x3, and x4. Okay, so what I'm supposed to do is I'm supposed to take f. Here's my f. So I'm supposed to take f of x1, which is 1.5, plus f of x2, which is just 2, plus f of x3, which is 2.5, plus f of x4, which is square root of 3. So you just plug this in your calculator and see what that equals. And that's your approximation to the actual area. Make sense? If I were doing this with left endpoints, according to my formula, I take the width of each rectangle, which is 1/2. But now I'm plugging in the left side, so I'm going to plug in x0. So I want f of 1, then f of 1.5, then f of 2, and f of 2.5. And again, we just stick that in our calculator and figure out what that ends up being. For midpoints, I'm supposed to take the width of each rectangle, which is 1/2, and now instead of plugging in the left endpoint or the right endpoint, I plug in the middle. So instead of plugging in 1 or 1.5, I plug in 1.25. You're plugging in the point halfway in between these two. Same over here, I'm plugging in the point halfway in between 1.5 and 2, which is 1.75. Then 2.25, and finally 2.75. Now, if you were to compute these and compare it to the actual answer, if you converted the answer to decimal form, can you guess which one, R4, L4, or M4, is actually going to be closest to the actual integral? Can you guess which one's going to be closest? It's actually going to be M4. And the reason is, if I actually draw the right endpoint one is going to be an over approximation. All of the rectangles are over the area. Left endpoints is going to be an under approximation because all the rectangles are under. But if I use midpoints, I end up getting something that has both a little bit of extra area and a little bit too little area. And those end up canceling each other out. Now, it's not exact, but it's a whole lot better than R4 or L4, and we'll see what I mean by a whole lot better in a little while. Okay? So that's how we do this with rectangles for right endpoints, left endpoints, and midpoints. That's not anything new. That's something that we've kind of seen before. Okay? All right, now what I want to do is I want to we're gonna make this a little more general. Rather than doing this with rectangles, we're going to try doing it with something else. We're going to do it with trapezoids. Okay, and why in the world would I want to do this with trapezoids? Okay, well, first of all, we need to review a couple things about trapezoids. Okay, so first of all, let's recall how to get the area of a trapezoid. Okay, remember, a trapezoid is this object where it's a quadrilateral. It has 4 straight sides, and 2 of the sides are parallel. The other 2 sides could also be parallel as well, in which case we get a parallelogram. And if they're parallel at right angles to each other, then we end up getting rectangles. So trapezoids are actually a special kind of rectangle. How do we get the area of a trapezoid? Well, if you remember from geometry, maybe you do, maybe you don't, trapezoids have a height and 2 bases. And the area ends up being the height times the average of the 2 bases. Okay, if you take the average of these 2 bases, what you end up getting is a length that's the length actually halfway in between. And if you take a rectangle of that height and width, this piece ends up equaling that piece, this piece ends up equaling that piece, and the area of this rectangle is actually the same as the area of the trapezoid. So the bases are the parallel sides, and the height is the perpendicular part in between. So it's height times the average of the 2 bases. Now you might think, why in the world are we talking about trapezoids? Well, let's do this in a different context where the trapezoid looks a little different, and then I want to show you how this connects to what we were talking about before. What if my trapezoid looked like this? So if I had, say, the bottom here was conspicuously called delta x, and I had a height 1 here and a height 2 here. So here you have to think of your trapezoid by kind of looking at it at a 90-degree angle. The area here, my height, if I'm looking at it at a 90-degree angle, my height is this delta x. This is supposed to be perpendicular here. My height is delta x, and my 2 bases are this h1 and h2, so it would be the average of those 2 bases, okay? So that's how we would get the area of this trapezoid. Okay. Now, how in the world is this helpful for me? Well, what we're going to do here, the idea is, if I have my function from a to b, I'm still going to cut up my interval into n equal pieces. Okay. This first place is x0, x1, x2, x3, all the way up to xn. But instead of taking the left endpoint or the right endpoint or the midpoint, what I'm going to do is I'm going to look at the left and the right sides, and I'm going to connect these with a line. Now, do you see how that's going to give me a really good approximation? If I draw a height here and a height here, and I connect those with a line, I'm going to get a really good approximation. Same if I do this and I connect these with a line. It's not exact, because the function's curved and I'm connecting with straight lines, but it's a pretty good approximation. Okay, so what we're basically doing is we're cutting the function up into pieces, and instead of using a curved thing, I'm approximating with a line. Okay, so we're going to, and you can see that this resulting thing that I get here is actually a trapezoid. It looks quite a bit like one of these. So we're using, instead of using rectangles like we were before, we're using trapezoids. Okay. So the area here, since we're using trapezoids, for the area, we're going to signify the area by calling it T sub n. So now the T means trapezoid. We're using n trapezoids. So let's get the area, to figure this out, let's get the area of this first trapezoid, and we're going to get a formula for this. Okay? So the first trapezoid has height, if you're looking at it from 90 degrees, the width here is delta x. And then I want to multiply by the average of these two bases. Well, the first base is what I get when I plug x0 in the function. That's f of x0. The second base is what I get when I plug f of x1 in the function. And now what I need to do is just average those. Okay. So that's what we're going to do. That's that first trapezoid right here. Okay. Is that clear? The second trapezoid is going to have width, kind of the height, delta x. And then I need the average of the two bases. Well, the bases are going to be what I get when I plug x1 in the function, f of x1, and then f of x2. So I'm going to average those two. The next one's going to be delta x, and you can kind of see the pattern here. I'm going to have f of x2 plus f of x3 all over 2. And then the last one is going to be, the final one is going to be f of x sub n minus 1, f of x sub n over 2. That's that last interval there. X sub n minus 1 and x sub n. Okay? So to get a formula for this now, to clean it up just a little bit, notice everything has a delta x in it and an over 2 in everything. So I'm going to pull the delta x and the over 2 out. And what's left here is f of x sub 0 plus f of x sub 1. That's those two things left over. Going to the next one, I've pulled the delta x and the over 2 out, and I'm left with another f of x sub 1 plus f of x sub 2. Going to the next one, I've pulled the delta x and the 2 out, and I'm left with f of x sub 2 plus f of x sub 3, and that continues on until I get to this last one, which is f of x sub n minus 1 and f of x sub n. Now we can actually clean that formula up by noticing that I have an f of x 0, and then I have two copies of f of x 1, and then I have two copies of f of x 2, and that's going to keep going until you have two copies of the second to last one. There's going to be one here and one here, just like everything that was going on here. So we've got two copies of f of x of n minus 1, and then one copy of the last one. So this is our formula for the trapezoid rule. Okay. So what you do is you take the width over 2, then you take one copy of f of x 0, two copies of f of x 1, two copies of f of x 2, okay, et cetera, et cetera, et cetera. Okay, so for example, going back to the previous example I gave you, if I said, here's this integral, approximate it with trapezoids using 4 intervals, or using 4 trapezoids. So here, delta x, so my width is from 1 to 3. If I'm going from 1 to 3, this is x0 up to x4. What this formula tells me to do is I need to take my delta x, which is 1/2, divide by 2, and then I take my function at x of 0. So my function at x of 0, is 1, plugged in here. Then 1.5 plugged in. Sorry. Let me just write this down in general first before I do it. So I need f of x of 0, 2 copies of f of x1, 2 copies of f of x2, 2 copies of f of x3, and then just f of x4, according to my formula here. All right, that's what I want to do. So I want to take a half divided by 2, well, that's a fourth. You need to take x0 and plug it in the function, that's square root of 1. Then I need 2 copies of x1 plugged in the function, so 2 copies of the square root of 1.5, 2 copies of the square root of 2, 2 copies of the square root of 2.5, and then 1 copy of the square root of 3. So if I put this in a calculator, this is going to give me a very good approximation to this area that we were talking about before. Okay, does that make sense? Does it make sense how to use the that formula to get that approximation? So using trapezoids, we're actually approximating the function with straight lines. Okay? And we've got a formula for how that works. Okay. Now somebody had a clever idea that instead of approximating the function with straight lines, maybe because that's good, but if the function's curved, I miss some of that curvature. So is there a better way to approximate it even than using straight lines? Straight lines give us trapezoids. And the answer is yes. It turns out that you can use parabolas. Now, I won't get into actually deriving the formula here, but the idea here is that every 3 points determines, just like every 2 points determines a line. So when we did this with trapezoids, let me do it with trapezoids just for a second. I'm going to do this with, let's just use 4 rectangles for right now to make this to make this clear. Okay, if I had a function like this, and so here's x0, x1, x2, x3, x4. Okay, if this is with trapezoids, what I'm doing is approximating with straight lines. Using my trapezoids there. Okay, so at each one of those, I would connect these points and I would get a trapezoid here, a trapezoid here, a trapezoid here, which is going to have a little too much area and a little too little area there, okay? If I did this with parabolas instead, so notice every 2 points determines a line. So there's a unique line that goes through each of those points. If I'm doing this with parabolas, it turns out, let's see if I can get kind of a similar picture here. Okay, here's the points. Okay, 3 points uniquely determine a parabola. Okay, so lines are determined, so 2 points determine a line. 3 points determine a parabola uniquely, and I'm not going to prove that. But it turns out to be true, and it's not that hard to prove. So the idea is, if I take these first 3 points and I ask which parabola goes through those 3 points, and find the area under that parabola instead of finding the area under the function, you can see that I'm going to get a lot of the curvature that I got in the function. I'm now going to get that in this parabola. If I can find the area under the parabola here, then that's going to give me an even better approximation than what happened when I was trying to find the areas using lines connecting the endpoints. Same thing now if I pick this collection of 3. If I find the parabola that goes through these, and I'm just guessing what that looks like. Okay, it might look something like that. You can probably see that using parabolas is going to give me a better approximation than using trapezoids here. Now, the scary part here when I start talking about take these 3 points and find a parabola that goes through them and then find the area underneath it, you might go, oh, that sounds terrible. It's actually not terrible. Maybe deriving the equations is not that fun. But it turns out that the formula, just like the formula for trapezoids, is pretty nice. The formula for parabolas turns out to be really nice too, okay? So just as a review, the trapezoid rule what I mean by the trapezoid rule is just the area of the trapezoids, was delta x over 2 times, and then I took the f of x0, 2 of f of x1, 2 of f of x2, and then 2 of the second to last one, and then just 1 of the very last one, okay? That gives me my approximate area using trapezoids if I'm cutting it up into n pieces. Using parabolas, we're going to give this rule a special name. It was actually invented by a mathematician named James Simpson, who was from England. And so this rule for finding the areas is actually known as Simpson's rule. And the areas using parabolas we're going to call that Sn, and the S stands for Simpson. but it comes from approximating using parabolas, using triplets of points instead of pairs of points, making lines. Now, in order for Simpson's rule to work, notice if we cut this up into three pieces, if we had x0, x1, x2, x3, I wouldn't have a triplet here. I would only have a pair at the end. So it turns out that Simpson's rule only works when the number that you're cutting up the interval into is even. Okay, we would need like 4 intervals or 6 intervals or 8 intervals. You can't just do this with like 3 intervals. Okay. In the case that you do this, the formula turns out to be, instead of delta x over 2, we end up with delta x over 3. And then what happens is you take f of x0, 4 copies of f of x1, 2 copies of f of x2, 4 copies of f of x3, 2 copies of f of x4, okay? And you keep going on this 4, 2, 4, 2, 4, 2 pattern until you get to the second to last one, so f of x of n minus 2. Take 4 of those, 2 of the second to last one, and then 1 of the very last one. So 4 of the third to last one, sorry. 2 of the second to last one, and then 1 of the, so it goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 1 are the coefficients that you have on there when you're doing this rule, okay? So maybe as an example with this same integral, if I ask you what is the approximation using Simpson's rule with 4, notice I had to do this with 4. I couldn't have done this with 3. What you're going to do is you're going to take your delta x here, or delta x before is 1/2, so it's still going to be 1/2. But we're going to divide by 3. And then we're going to take 1 of the first, then we're going to take 4 of the next one, square root of 1.5, 2 of the next one, 4, now I see that I did this wrong. 4 of the second to last one, and then 1 of the last one. I'm sorry, I messed this up. Let me fix this. It goes 1, 4, 2, 4, 2. I can't count this right. It's supposed to be symmetric. So the second to last one is 4, and the last one is 1. So this is actually supposed to go 2, 4, 1. So it goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So I apologize that I messed that up. It's supposed to go 1, 4, 2, 4. So in this case, it's going to go 1, 4, 2, 4, 1. So apologies for that. That I kind of messed that one up just a little bit there. Okay. All right, and that is how you do Simpson's rule. And again, we would throw that in a calculator to figure out how close of an approximation that is. Okay. One last note. So your formulas for all of these, let me kind of bring all of these formulas together just so you have them. So for right endpoints, it was delta x times f of x1, f of x2, all the way up to f of xn. Left endpoints was delta x times f of x0, f of x1, all the way up to f of x sub n minus 1. So that's right, left, midpoints, delta x, and then what I do is I take the point halfway in between x0 and x1, that's the average, the last pair. Okay, these are all using rectangles. So I've got right, left, and midpoint. So those are just using rectangles. And then I have the trapezoids. And the trapezoid rule worked by saying delta x over 2. And then what I do is I take f of x0, 2 copies of f of x1, 2 copies of f of x2, 2 copies of f of x3, all the way up to 2 copies of the second to last one, and then the last one. Okay? So again, this is using trapezoids. One thing that's very interesting, you may want to think about this. I'm not going to ask you to prove this, but it's not that hard. The trapezoid rule is actually the average of the left endpoint and the right endpoint rules. So if you take the left endpoint and the right endpoint rules and you average them, you actually get the trapezoid rule, which is interesting and also can save you some time if I ask you to compute all of these. And then the last one that we have is Simpson's rule. Simpson, so S of n. And that was the formula that I just gave you, delta x over 3. I take 1 of the first thing, 4 of the next thing, 2 of the next thing, 4 of the next thing, 2 of the next thing, all the way up to 4 of the second to last thing, and then just 1 of the last one. Okay, and again, what we're doing there is we're approximating using parabolas on triples of points, groups of 3 points each. Now you might ask, in general, which of these approximations is the best one? I'm not going to get too far into there. The book starts to talk about error. I'm not going to get too far into the error issue here. But one thing you should just know is that in general, there are special cases when this isn't quite the case. But in general, the Simpson's rule is the best. This gives you the best approximation. The next best one is actually midpoint. That's the second best. Trapezoid is third best. And then left and right endpoints together are kind of tied as the fourth best. They're kind of almost the worst. Like I said, I won't get into this too much as to why this is the case. But especially as n gets big, Simpson's rule gets very fast, very close to the actual area, to the actual definite integral, to the area that we're trying to approximate. The error on these turns out to be, I don't know if I want to get into this. The error, well, let me just say this. The error for Simpson's rule, well, the error for both the left and right endpoints is basically a constant over n. So as n gets big, like if n goes from 10 to 100, the error shrinks. It shrinks by about a factor of 10. For these two here, the error for both of these, the error turns out to be another constant over n squared. So when n gets big, this actually shrinks much faster than this one does. Down here for Simpson's rule, the error is actually a constant over n to the fourth. So this actually shrinks really fast when n gets big. When n goes from 10 to 100 here, this thing shrinks by a factor of about of 10,000. So this, in general, again, Simpson's rule is the best, followed by midpoint rule and then trapezoid rule. And then right and left endpoint rules are, they're okay. Now when n goes to infinity, all of these approach the actual area. But we're not letting n go to infinity here. We're actually just approximating using some sort of numerical thing. So, okay, so you'll have some problems where basically it'll give you a specific area, a specific function on an interval, and it'll ask you to do these approximations, compute what they are, and maybe if you can actually do the integral, it will tell you, do the integral, figure out what that is, and compare to see which one is closest, and chances are you're going to see that Simpson's rule gets really, really close. Okay, so take a look at the homework. The homework for this section is not due on Thursday, tomorrow. It's actually due on Monday, but this is just to give you that opportunity to be able to do it. Have a great rest of the day, and I will catch you tomorrow. Thanks.